Hey guys, good evening, everybody. First of all, congratulations. We had the last EAS talk, and this is the last talk of OSPM. So you made it. And just so that I have your attention through this talk, I have a bribe. Good questions get chocolates.
Good batch questions, yeah.
Oh, we've been eating too much. I mean, nobody else got this.
We're all full. We're full, so it's a good idea.
It's going to get you sugared up.
I just had donut.
You don't need more sugaring up. So anyway, Dhaval, I was working on the schedule a while back. Then I went over to the dark side. And then I looked at virtualization for a while. And now I'm back here. And in the time I was away, Peter wrote a new scheduler. And I think he was really thinking about me when he wrote this because he based it off a paper. So I could read the paper, and then I could go see what was happening. And so that led me down the memory lane, which led me to this yesterday. This is the first time I came to Uhldingen, to Thomas's house. There's no gray hair. And we had fun. And if you stayed the entire night, you had room in the garden to go to sleep. But thank you, Thomas. And just for that, I have a chocolate for you. So, no, it's not American cheese. So
There's no American chocolate either.
So EEVDF. I went, I started looking at the paper. Now, this paper was published in 1995, so 30 years back. And Linux came about in 91, so 4 years younger. I went and looked up Wikipedia to see what was happening in 95, and it said Linux was ported to DEC Alpha and Sun Spark. And just for context, I was in primary school back then. More importantly, SMP support had still not come into Linux, which is fun, when we talk about today, because my phone's more powerful than the 386 I had back then. They're there everywhere, and they're not necessarily even symmetric. They may be asymmetric. So, I came back when I started looking at the paper and started looking at the code. The question really was, how has it been adapted for today's world? And then, has it been adapted for today's world? Okay, so before I start going into what was happening, I think it just makes sense to look through what the paper said and the paper's definitions, simply because that's not what we do in the scheduler. So these bits, when we look at, that's what the paper says. And one of the things I got the impression that people have not read the paper, so maybe it may be a good idea to go through it. So they had some definitions. There's the terms, there's weight, which is similar to CFS. And essentially, that has an impact on how V runtime scales. So greater the weight, slower your V runtime scales. And then, when you say share, it's not what we had in CFS C groups back in the day. This is actually the share of the total system weight. So, if you pick a task I, it's weight over the sum of the entire system. And then they define something as ideal service time, which is the amount of time you should have received, assuming every task could run at the same time. And so with that, and so with that, you could define lag when you take the difference between ideal service time and your actual service time. And so once you have lag in place, you can now start talking in terms of what the algorithm is. Now, they try to keep it as flexible as possible. So, and the way the algorithm goes, the way paper describes it is a client issues a request for service. And what they go ahead and then mention is that it doesn't need to be, the client itself. Somebody can do it on behalf of the client. And in this case, that's the scheduler. And when you make a request for a certain duration. And since the scheduler is making the request for you, that could just be the time quantum, the scheduling quantum that you have. And then, with that, they then defined service time, which is total system time scaled by the weight, and then system virtual time, which is actually a bigger number all the way from a smaller number rather all the way from 0. And so once you have system virtual time and service time, then you can start looking at virtual eligible time. When is a task eligible to run? And that is the current system time, the virtual time, and then that you add, you scale your service time, last time, by weight, and then that tells you when you are eligible to run. How did that mouse pointer move? And then the deadline is defined as when you're eligible, and then you add the total request duration, which is in wall clock time, and that you scale by weight, so that gives you virtual time. And that's your deadline. Now, this is how they have defined it, but in reality, it's actually your actual virtual deadline will be VD plus Q, where Q is your quantum. So it's hand wavy. And the algorithm is straightforward. If you're eligible and you have the earliest virtual deadline, you get to run. It's pretty straightforward. So, this is an example that they had in the paper. And I'm going to walk through that. Funny enough, the paper actually had a mistake in this diagram. I realized it much later. But, at wall clock time T0, the first task comes into the system. It enters the competition. It has a weight of 2 and a request length of 2. So, you go back, weight of 2, request length of 2, 2 by 2. Your deadline is going to be at +1. So, eligible at time t is equal to 0, virtual time equal to 0, deadline of 1. And at this point in time, wall clock time 1 is equal to half in virtual time, because weight of the system is 2. At wall clock time 1, a second client enters the system. And so it has a weight of 2 as well, and a request length of 1. So its deadline is 1 divided by 2. So, half virtual time, deadline is 1. And at this point in time, you'll notice your virtual time has started scaling at a different rate. So, and now you just follow the algorithm. Its deadline is at time 1. It is eligible to run. It runs. Next request comes in, is queued up by the scheduler. But, we are at virtual time 0.75. So this guy is not eligible to run. We go back to the first client. Its next request comes in. It's eligible to run. But this one has got an earlier deadline. And so on, right? So that's essentially what's happening. Now, this is a very simple static example. The paper itself was very, very light on how it handled dynamic systems. So by dynamic systems, it's when a task is coming in, leaving. They asked 2 questions, and I added a third one. The first question that they asked was, what's the impact of a client leaving or joining the system, and when we reweigh the system? And the second question was, when a client with a non-zero lag leaves the competition, where does it join in? And so these are like 2 really, really important questions to answer. Now, you have to think about what is the impact of a client leaving on the system with the entire virtual time. So remember that you have the rate at which virtual time moves. That is inversely proportional to the total weight of the system. And when you have a task that has a positive lag, that means it is owed some time on the system to run. The other possibility is that you have negative lag. So negative lag means you ran longer than you should have, which means you're not eligible to run. You're not eligible to run. And so you ran for some time and now you get DQ'd. What does that mean for the rest of the system? Because with virtual time going back, that means every other client in the system is penalized. So that's the question that they went and asked. And then what happens when you join? Same thing. When you come in with a positive lag, you're going to get to run immediately or sooner. So that's possible. It's going to affect other clients in the system. And if you have a negative lag, maybe you need to wait longer, but then that has other problems. And then changing wait is pretty straightforward, right? That's a client with wait W old leaves the system, and the client with W new joins the system. So as long as you figured out what to do with leaving and joining, it should be easy to answer. And then, how much of this really translates to today's systems? I mean, we have not thought about SMP. Do we really want to bring all the negative lag into the system? So on. It should just translate, but that was a question I wanted to answer. So the paper, while it was very light on details, did have a few proposals. They said we're only going to take care of negative lag, and this is how we're going to scale or update. And yes, it's going to impact the system, but that's okay. It should eventually catch up when the client rejoins the competition. And they said that if you have positive lag, we're just going to treat that as zero lag, which means you're eligible to run, and so on. Any questions? Peter, did I give a good description, or did I miss something here?
It's okay.
Okay, so
what if a task sleeps for a long time? The VDT would become smaller compared to the other.
Right. So those are good questions to answer. All I'm saying is this is what the
I asked this for the joke.
yes,
Just ask.
Oh yeah, definitely ask questions.
There are real chocolates. Okay, so just coming back, the paper is very light on these details. So part of this exercise is also to document what we are doing in Linux and why. Okay, so
I'm sorry, I asked about. Did you mention the with the lag when you did you? I think you implemented it already, right? Where while you're off the run queue, you actually it's as if you
the delayed DQ. Yeah.
The delayed DQ. Well,
Yes.
where you lose your lag as you.
Yes.
Well,
Yes.
delayed DQ. Yeah.
Yes. Yes.
Yes.
What? It's very much not part of it.
That is not a part of the paper.
Right. So like I said, that's where like I said when you don't get to do that, when you come in and you have lag, that's why we have issues.
Was it good?
And that was even a question. That's not even honest.
People will just start saying random stuff.
No. I mean, that was a good thing to bring up. So, I want to step back a bit. When I started looking at EEVDF, and since it's based off an academic paper, one of the things I realized is, hey, they're describing the scheduler to us and properties that it must meet. And this took me back to, was it 2019 or 2018 OSPM, where we were talking about invariants for CFS. And that would be a lot of reverse engineering. Except, here this paper just gives me a ready-made set of invariants. So I went back and I said, okay, maybe it's time to start writing some of these tests, start looking at the paper and see whether we're doing that in the scheduler. So coming back to the paper has defined two things, a steady system and a steady interval. I am going to admit that I really did not find a lot of use for the steady system definition. It's not
This is what academic papers often do, and it says, if you assume this, everything is easy.
Yes.
I like some of the academic guys laughing the most.
By definition, only hard cases go away.
Yeah, I mean, it's easy. You just write define reality.
Chocolate speed.
So now we have a process. It's coming by demand. Okay, so, but I did find the second definition a bit more useful, in the sense that an interval is steady when all the events occurring in that interval involve only clients with zero lag, and the way I read this, and it makes sense for me, is every client has crossed the zero lag point. So then this, going back to the whole idea of invariance, the paper defines a couple of lemmas. Well, actually more than a couple of lemmas, but I'm going to just stop at the first two. The first one is if a client has positive lag, it has a pending request, and I think that's fairly obvious. And the second one is at any given point in time, and this is the whole point of the steady interval, the sum of lag of all active clients in the system is 0. And so I went about, let's try to see what's actually happening in code. Now, when I started writing this, I'm not expecting it to fail, I'm expecting it to pass. So what happened, the scheduler, it really doesn't track lag directly. What it does instead track is a zero lag V runtime, and then you use that to compute the lag.
No, so
Go ahead.
we only actually track the v-runtime time of the entities. The
Yes.
zero lag point is inferred
From that.
from all of those. Yeah.
Okay. Right. I mean, I think the reason I went in that direction was that you have average V runtime, so I can compute that. So that's what's being tracked.
It's an artifact of the individual v-runtime.
Okay. Yeah. So what I did was I put a check in EEVDF and just check are we left of the zero lag V runtime. This is an obvious test. It should never ever fail. So I did wonder, is this a valid test? Because this is not exactly testing what the lemma says. The lemma says the client must have a lag greater than 0 to have a pending request. I'm testing the opposite. I have a pending request, therefore the lag must be greater than 0. But I think that was useful because
When we first start, if you have one task, that means its lag would be 0, right?
yes.
So then you pick it, and then the 0 would be the V runtime of 0, or would it be less than?
Yeah. So yes, it should be equal to.
So that would be
That's
false.
yes. I think that's a
That should
mistake.
be
I
less than or
made.
equal to.
Yes, that's a mistake I made. But yeah, the test itself is testing that it's failing if
Yeah.
the V runtime is greater than average. So I should correct this. Anyway, so I did wonder whether this was a valid test or not. Because your pick EEVDF is always going to pick from the left, which by definition is going to be left of your average V runtime. But remember this is an invariant. It should always be true. We should never break it. And so if we do, there is some subtle error somewhere. So we should always pass.
So Dhaval, since you mentioned left and right, so the tree is sorted by the deadline in the implementation. So is that always true for you? That left means that you are less than the average deadline. Does that mean true?
So Dhaval asked me this yesterday, and I forgot the details, but so we flip the tree on its side, it will have a simpler iteration. It is semantic equivalence. And I want to say Josh, but it might have been the other one from Google. He actually implemented both and had a user space test harness for the whole thing. But Yeah, it's basically the same thing, it's just a tree iteration ends up being simpler if you flip it on its side.
So we do consider left is in some sense.
Mostly in my mental model as well, it's as described in the paper, left is left free runtime, right is more free runtime. But the actual data structure, as it flipped, then we sort by free runtime, by deadline.
Was that a good question?
So if it's not eligible, is it in the tree or?
That's in the tree.
But if it's got the.
Very arbitrary.
Next deadline, that be not eligible, but.
So the tree iteration will end up in non-eligible tasks.
Okay, so the non-eligible always would be okay. As I said, we were doing on deadline and not virtual runtime.
So this is an augmented red
Yes.
tree, it's not a pure red tree.
Okay.
So it's a red tree combined with a heap. So at every point you have two things. If you have the two children, and those are sorted per the red tree, but you also have a heap sorting. So in this case, this would be the left and right child would be a lesser and greater deadline. But the heap property is, I think, the smallest in runtime, and then the parent's smallest free runtime entity would be the smallest of the node itself and its two subtrees. So you can combine a binary tree walk with a heap walk.
Okay, so it
And
makes you
this
stay inside
combined
the one.
is like a 1.5 dimensional data structure, and you can do these queries. And I think the setup in the paper does require more iteration in the tree. This is slightly more complicated. If you put it on the side, it's less iteration to find the thing.
I mean, there are other additional complications as well in the paper implementation. In any case, this is an invariant, so it should never ever break. So I do think it's a useful test, but yeah, it should always pass. And then, you know, I did something for the second one, which, as you remember, at any point in time, the sum of lag of all the active clients is 0. So we don't track lag explicitly as we talked about. So we just use the 0 lag V runtime. And that's kind of interesting because, you know, there's a big fat comment on top of all the average V runtime functions talking about how you, Peter, modified some of the math there, simplified it, and you know, that's what it's based on. So this is not what I do right now. This was when I actually wrote the code for when I wrote the slides. Sorry, I wrote a module, exported a bunch of scheduler internals, and then when I was doing this, you know, remember 1995. So no SMP, no C groups.
Yeah.
Make Linux great again.
Come on, that was not even the question.
Come on, he deserved one for that. Okay, of course that has changed. I have updated the code to not be a module, but also, you know, walk through SMP, walk through trees and C groups. In any case, what I did was I walked through the RB tree and I pulled out each entity's V runtime, you know, counted the number of tasks, did the division. The comment that Peter had there had me a little worried that it may not be precise enough, but you know what? To my surprise, it has been 0 in every single test I have run. So, you know, Peter, for that.
Ooh, you guys are special.
Yes. that was actually impressive. But yeah, I mean, again, you know, is this a valid test or not? That's a question that we need to answer. And I think that this is valid because what we are doing is we are calculating all of these numbers post the scheduling decision being taken, and the scheduler itself is updating it at runtime as it's making the decision. So I do think it's valid, it's valuable. Again, it's an invariant, so it should never appear. So these are two that I have complete. And then, there are more lemmas that they define that I think are going to make interesting tests. It's kind of where, I don't know if, in the beginning I mentioned the effective deadline is actually D plus Q. This is where they define it in a steady system. The request must be completed between the deadline plus Q, which I don't know why they didn't define virtual deadline with Q in mind to start off with.
I have a question on the previous slide. Maybe not chocolate rosy, but we'll hold off on chocolate for a little. So basically I was wondering, like, I don't know how you're testing this, but like, say you like take like 3 tasks and you run it for a long time, right? I'm wondering, like, is like any of the additional like overhead that has to do with interrupts or other reasons, like eating away time, does that also affect the lag, the sum of the lag? Or
no, because it's a property of just the CFSRQ. Each CFSRQ has its own VRun time or average VRun time.
Okay.
And so interrupts are not accounted there.
Oh, how do you does it handle like real-time tasks interrupting and stuff like that? It's kind of
My module.
yeah.
In this case, I launched a real-time thread. I disabled interrupts in this example. So yeah, and first RT99.
So
Yeah, but sorry, but like like just theoretically, like if you just think about what lag is, you're basically robbing the time that something else deserved to run, and you're giving it to something else, right?
well, is that, or is it because it's like virtual deadlines,
Yes.
it's virtual time frame? So
Yes.
it's just lag. I just change the virtual time frame. This opens up.
So
Does it- the
you're making the
virtual
same
time-
mistake I did.
And
Okay.
You are thinking in terms of wall clock time.
Yeah, but
So you need to.
Makes it hard.
The world, the EEVDF world is limited to just that CFS run queue
okay.
for just that virtual time.
Okay, so you're talking about virtual lag or whatever.
Yes.
Okay.
You shift the whole thing until your real-time task completes.
The time
Okay.
scopes.
Time stops.
Yeah, that makes sense. Yeah.
So this is only with respect to the parent task.
Yeah, okay.
No
Okay, got it.
previous.
Okay. So no chocolate?
So that was actually a good question because I also made the same mistake.
I blame Tommaso for me making that mistake, thinking in terms of real time all the time. Okay, so this now is what I want to develop as my next test, but this is interesting because, Peter, you have already clamped the maximum lag we can have on the basis of this.
You can, so I did this because the C group reweight had some numerical stability issues, and I saw it accumulate errors over multiple reweight passes. And if you let the lag grow too big, it goes funny in the head. Bad things happen. So yeah, I clamped it. You can
So is this useful to test for?
probably,
just-
but in a limited situation. So the no C group, no S&P test case, you can
But-
for example, increase the clamp I have and see if it escapes.
Okay.
In a limited runtime situation.
Sure. I mean, the other thing also to keep in mind is we could also just limit it to the leaf CFS run queues because it's a.
Sure, but yeah.
Okay. Yeah, so.
So I would try and do it without C groups, but the problem was the reweighting.
Yeah, yes, but the reweigh will be at the root run queue, right? Root C group, not at the leaf
It's
C.
like a hierarchy. I mean, it's purposeful way.
Okay. Okay. Sure. So Okay, I should take a step back and actually talk about the theorem before jumping into the test itself. So what they claim is that in a steady system, the lag is bounded and that this is a tight bound. So the lag is between minus R and the maximum of R comma Q, where R is your request length, so the maximum length request you have from a client, and Q is the time quantum.
Q, sorry, yeah. So what I'm curious, what have you put as a Q quantum?
Sketch slice.
Are you sure?
Yeah, so our slice request is basically the R in the paper. It's the request.
Yeah. So Q becomes interesting only when R changes, right? Now, when the scheduler is picking a task for you and issuing the request, R is equal to Q.
That's probably where I've never been able to define what the Q was for our implementation. Because they said the Q is the tick.
Yeah.
More or less.
Yeah, more or less. I mean, when you look at the definition, Q is the minimum slice of execution where you can't be preempted. And after Q, you should normally trigger to see if you should switch to another one.
Correct.
That's the tick.
Yeah.
No, because if you start running in the middle of the tick, you can be preempted at the tick. But yeah, that has always been, because I mean, yeah, for me, we don't have a well-defined Q.
Yeah, so the worst case Q we have is tick.
Yes.
So consider this Q.
So yeah, this one is the next one I want to. Yes. These are bribes, by the way. Okay. So yeah, I mean, this is the next one I want to go implement. They had a fifth lemma as well, where again, the lag of any client is bounded by Q. You should never have lag greater than Q, which I think should make sense. With that, I have discussions here, but also a few thoughts on where to go next. So the delayed DQ, for example, is an interesting bit where it is doing something different from the paper. And I think it would make sense to document what the bounds should be for that. And also whether when it is eligible to run, it is at the right place or not. And maybe we just document it. Maybe it is not. But thoughts on what else we should be looking at.
What do you mean by what?
Invariance, in terms of invariance, because the changes made to the Linux scheduler. Sorry, Masu.
Okay, just a silly question. So as this, if I got it well, the original guarantees you have, basically you keep respecting them, the fairness guarantees, you keep respecting them in the individual run queue on a single CPU. But what about if you look at the entire system, shouldn't we aim for a system-wide fairness property, considering multiprocessors and all the stuff? Or shouldn't load balancer be aligned with whatever we should be aiming for?
No, and that is a future goal.
Oh, I was expecting that is a very good question.
It is a very good question. More or less generalize.
You get the whole back.
How many are remaining?
There are 3 left, so.
Actually 4. There's a 4th one here. Sorry.
I don't know, maybe there might be a way with these theoretical guarantees to some way tweak or at least drive the design of the load balancer.
Right. So Tommaso, this is exactly what I want to do, right? Figure out what your bounds need to be.
I mean, that's actually kind of like what Mux Scheduler kind of does. It has like multi-queue. I mean, it actually tries to keep everything in sync and then just have everything migrate. So if it doesn't have a load balancer, it just lets it naturally move things.
Okay.
But so anyway, to answer the other question you had, right? First, this paper is from a time where SMP was not a
was
thing.
no problem, yeah.
Right. So I mean, there are a couple of other papers after this that are on my list. There's a W squared FQ paper. Peter, you mentioned there was a EEVDF block scheduler paper.
Sorry, did that, right?
No, that was a BFQ.
So, but no, that's just BFQ. So BFQ started out as EEVDF.
Oh, okay.
They started out with, and then they ran into a whole bunch of issues. And I have no idea where they ended up. But one of the things that they mentioned at the time, because I already had the EEVDF patches floating around at the time, was the DQ behavior. They ran into that well. And I think for the block, they had a separate tree where they tracked these entities.
Okay. So yeah, I mean, so those are two papers, but how do you do multiple entities or multiple queues? So the okay, so I haven't yet gotten the SMP stuff fully working, but my intuition says that each one of these CFSR queues should be internally consistent.
So they're currently fully partitioned. So they're
Yes. 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 So then the next interesting question is how you, I mean, yes, you're bringing in with the same lag when you migrate and so on, but is there something better we can do? Right. And that's kind of where writing a test helps, right? And trying to document.
Yeah, so I think I thought about shared free runtime when we did the whole course scheduling mess. And I can't remember my ruminations exactly, but I got myself into a real twist once I started to consider affinities.
Okay. Oh, yeah.
Because virtual runtime really only runs if there is contention. Without contention, it has no function.
Okay.
But what is contention when you consider affinities? So, yeah.
Well, maybe multiples. You mean overlapping or
Free
not?
runtime offer.
Like one task has 1, 2, 3, the other one.
So you have two CPUs.
2, 3, 4.
So you have two CPUs and any number of tasks you want, and they're all assigned to one of those CPUs. Then what is the shared read runtime of the CPU that is idle?
Yeah.
It's just really
And another thing I want to,
any infeasible way scenario you can construct, and this is the simplest, turns into a nightmare.
and then another thing I want to do is the SCAD eBPF folks, your EEVDF implementation. Do you have like a global run queue, or are you just basing it off what Peter's?
Most of them we use a global run queue.
Right. And then, I mean, the EEVDF implementation specifically, are you basing it off what Peter has done, or are you basing it off the paper itself?
I would say paper.
Okay, so then
It's-
you're
it's
having
not
like a
perfect. I
global
mean-
V runtime.
Yeah,
And not, so then that's another.
But we don't have eligibility in most of this case. Well, we don't have an SCX EVDF right now. It's
Sure.
But we follow the V runtime concept.
Right.
We don't have right now. There's not a scheduler that implements eligibility.
Yeah.
There's global share queue unless with some declination you may have per node run queues. But yes, I would say
Right.
in your case, you're at
right. So what I am thinking of is maybe a SCAD-X EVDF, which has the concept of a global V runtime. So we do what the paper's math says, as opposed to Peter's math.
Yeah, that would be nice. It's actually my secret to-do list stuff to do because I want to. But the reason, so I haven't done that because if I if I publish something that is called SCX EVDF, people are going to start using it and compare with EVDF,
Sure.
like the in
Let's call it theoretical EVD.
Yeah.
Be careful of numerical stability. The problem is that your individual vRun times are divided by weight,
Yes.
while your global vRun time is divided by sum of weight, which is a bigger number. So since we run
No.
the fractions are different.
Yes, but it's scaled by the weight of the task. Do not forget. So the entity, the task vRun time is scaled by the weight of that task. So it's Wi into integral 0 to t or t1 to t2 1 by.
But time divided by weight.
So,
the W is a. The whole point is that you have two divisions
Right.
with a different
Yes.
divisor. So your remainder is different.
No, your
So
divisor.
if you truncate and do not carry the remainder, you will drift.
Wait, the divisor is the same, right? What am I missing here? So your system virtual time should go a little slower, right, as compared to your.
So this is system virtual time.
Yes.
Task virtual time.
This is the task virtual time, right? It's still having the same numerator here. Only thing is that system time is starting from 0, whereas, so system time is what has been the time since the beginning of time, whereas the service time is for the interval you ran that you scale. So you should, yes, I know, it hurts my head as well, but you should, essentially at some point in time, V of t will become greater than the service time, or what's the actual vRun time, and then it should be eligible to run.
Yeah, I can't remember. So what we do is the virtual time is divided by the single
Yes,
weight.
yes, that's what you do in Linux. But the paper describes something else. This is the math I want to do inside the eBPF one, just to see how much we differ. It may be a fool's experiment, but it doesn't hurt to try.
Be careful with the divisions.
Yeah, okay. I think we are out of time, so.
2 minutes.
More chocolate?
You have more slides?
That was just cute. I was like, I'm done.
I want to. So again, it's out of the paper scope. So what happens in this picture when you have frequency switching over time? So what are you checking? Or at least how do you define the fairness properties? Are you checking the actual progress of the task? Yeah, scaled by frequency, or are you checking?
Yeah, in 1995, the master.
So we give back.
Yeah, no, I get how it's done. So,
So
is there anything that scales things, or just don't care? I don't know.
So the run-to clock is scaled by everything. We scale by.
If you're based on vRun time, that's already modeling any potential scaling that you have because you're.
So the run-to clock is already scaled.
Yes.
Yeah.
So in this case, we are ensuring if there's like dynamic frequency switching, we are ensuring that this lag is guaranteed in the domain of the progress of the real progress of the task, not really in time, because in time it becomes pointless.
Yes.
Okay.
Yes. Virtual time though. Okay, thank you everybody.
Thank you.
You can continue these discussions later. I'll hope to post the code sometime soon.
This, by the way, is also a problem in global, because what is the time?
If you,
There's no shared
yes.
time base. Because CPU can run at different frequencies, you can have different holes due to a real-time task. There's a shared concept of time between cores is a headache.
Yes.
So
Yeah, but for comparison, you can do it on a Unit processor.
Yeah, everything works. Yeah. Again.
So this is one of the things that.
No, I mean seriously for.
Yes, no, for verification.
Just compare it to
Right, yeah. Yeah, yes, but the interesting bit is to figure out,
I'm actually
I mean,
using the global clock.
Yeah.
So like, but if I use in one of the earliest versions, I was using like the per CPU thingy, and it was like the math was completely off because like jumping across CPUs was a nightmare. So I was like, okay, let's just use like a fixed global runtime, and that made everything better. Yeah, yeah.
So, I mean, Thomas, there is a goal when I say I do want to have it, working on SMP and do the comparison SMP. It is, part of this is to document where we have deviated from what the paper says, where have we augmented further. We don't want to lose that information. And we also want to be able to continue testing that none of those assumptions are broken. So there is a point to doing that. It's not just comparison.
I know we are like short on time, but in the 2 server example that you showed, right, today's scheduler doesn't actually switch at every tick, mostly because we have the run to parity bit. Because until we hit the deadline, we keep the task around, right?
Thomas.
For GQ? GQ or
So if we don't have any wake-up event, we run until the deadline. Do we check for eligibility? We don't.
No, you just need to be eligible at the time of picking the task.
Yeah, exactly.
Yes.
But
Even in this algorithm.
No, in the 2 server example that you showed, right, if nothing wakes up, you run the client until you hit the deadline.
Correct.
Yeah.
Yes.
So I mean, just because the red task was eligible
Yeah.
came up,
And had an earlier, it was, yes.
Yeah.
we don't.
Yeah. You could have run it a little later, yes, depending on how it was set up. But yeah, I just pulled up the example from what they had in the paper.
That's another deviation from what the paper.
I mean, no, not really, because all the paper cares about is you're eligible and your deadlines are yes.
Okay.
So somewhere on LPML there's a C file, a user space thing that makes pretty pictures of this.
Yeah. Okay, thank you. I will find it. But you're just giving me a look, so thank you, everybody.